Hello everyone, my name is Vitaly Bragilevsky. I work as a developer advocate at JetBrains, and in this talk I want to share you my approach to learn Rust via implementing algorithms. If you want to follow this talk, here you can find these slides available, you can download them, and then there is also a link to the GitHub repository that I will use during this demonstration. I will show you the links once again later. So, when one wants to learn programming language, the first path is to read books. You can find a lot of books in our Rust community. There is beautiful The Rust Programming Language book. There is also Rust in Action. There is Programming Rust book, and there are many others. You can easily find them. Then you can also explore examples. When you look at them, when you play with them, and you try to do something on your own around those examples. But I'm a proponent of the third path, namely solving problems. You just find problems everywhere, and then you try to solve them, and then you learn Rust in the process. There is also another path. You can develop your own projects, but I believe that this can be quite complicated when you are doing your first steps learning one programming language. So maybe you should keep that path for a little bit later. Okay, now let's focus on this solving problems approach. Where can you get all those problems? Well, the good news is that there are many platforms out there. You can go to LeetCode or HackerRank or many other platforms like that are also available. You can get their problems and try to solve them. Apart from problems, these platforms also give you automatic checks. You can test your solutions. They can provide you with some information about timings, about memory usage. They can give you hints. They can show you correct solutions and you can compare them. You can also participate in discussions using forums and other features from those platforms. But there is one thing that is not available there. These platforms never give you real software development experience. Maybe it's not that important when you just start learning programming language like Rust, but this is really important. And there are two other important things when we are thinking about using all those platforms. The first thing is that we have different goal. We want to learn programming language, we want to learn its features, libraries available, or broadly speaking, its ecosystem. So our goal here is not to solve these particular problems. And if you have different goal, then you have to use another approach to achieve that goal. And then you can also think about this. We do want to get used to professional tools. We want to use IDEs. We don't want to be stuck in those websites' interfaces. Okay, I suggest switching to another approach. First, you should use a professional IDE. It can be Visual Studio Code with Rust Analyzer, no problem. It can be some tool from JetBrains, that's fine, with IntelliJ Rust plugin. And then you should implement those algorithms, solve those problems, not like those are problems, but as if they are critical software components. And this idea is very important here. You develop software professionally and not just solve some easy or maybe hard problems. There are several components which help you to accomplish these goals. You have to use version control. You have to create Cargo project with both library and binary. I will tell you later what does it mean and why do you need that. You will have to use more than one module. You will have to write your own unit tests. You have to use integration testing. You'll have to come up with some sort of benchmarking. You'll have to profile your programs and to check their memory usage. All these components are very important. Okay, that's enough talking, I believe. Let's look at the sample repository. I will use CLion, but as I said, you can use whatever you like. So let's go and see what I mean when I require all those components in the learning process. Here is a problem I'm trying to solve. It's LeetCode's problem 22 about generating parentheses. You are given with n pairs of parentheses, and you need to write a function to generate all combinations of well-formed parentheses. Here you can see some small examples. But I won't dive into the details of this problem. We're not interested in that, actually. I want to present you how I use all those components of the learning process. Let's start with version control here. Let me open the window with version control information. Here you can see that I use commits to record every step of my work. Why do I need that? Well, because I need to have a chance to revert back if I write something wrong. You know, it's very easy to experiment with the code when everything is recorded, when you can freely throw away something if it doesn't work out. So I have a master branch, and I can create different branches to check this and that. Like here, I've created optimized branch, and you can find it in the repo, where I try to do something more efficient. But if this attempt fails, no problem. I just throw it away. I shouldn't think about that. So we need version control to make any changes to our code without any hesitation. If it doesn't work, just throw it away, go to the step back, and you have no problems. That's why learning is made much easier when you have version control in your project. Let's look into the project itself. We have README file, of course. We have Cargo TOML file. It's a Cargo project after all. And we also have library crate here. The root of that crate is defined in librs. And we have binary crate here, main.rs. Speaking about library, we have 3 available implementations here. We have breadth first search solution, we have depth first search, and we have subcombination solution. All these 3 algorithms are described in the README file, and I've adopted them from the LeetCode. So, library contains 3 implementations of that algorithm, and we are using modulus for every implementation. Library crate, main crate. I also have here tests. These are sort of integration tests where I compare different solutions with each other. They should give me the same results. I also have benchmarks here in the project. I can run them with Cargo Bench. I have Dockerfile. Maybe you don't need Dockerfile, but I need it here in my project to run this project in different operating systems using Docker. I can run it in Linux, and I can try other Linux tools to check all these implementations. So, even a small project is much more comfortable to work with if it has all these components: modulus, library and binary, tests, and benchmarks. Let's look into these components one by one. Let's start looking into the library crate. Here you can see only 1 submodule implementations. Let's go there. This module defines 3 submodules for 3 algorithms: DFS, BFS, and some subcombinations. This module also defines the general type for all these functions. And this is a very important idea. All our functions solve the same problem. And that's why they need the same interface, so that we can use them interchangeably. We can compare them. And this function takes size of the problem as an argument and gives us back a vector of strings. So same interface for all 3 functions. And we also can define a slice with all the implementations. In this problem we have 3 implementations, so it's a slice with 3 elements. And we can use str type to link to them: DFS, BFS, and subcombinations. Let's look into all of them. For example, this is generate parentheses using depth first search. It's a small function, as you can see, but it calls DFS functions, which is recursive, and it solves this problem quite quickly. There are also other problems, other solutions. For example, BFS. It's quite a long one. It requires a lot of stuff with vectors, so you can try to check your understanding how structs work, how mutability works in Rust with this implementation. This is something that was not required in other implementations. Okay, and subcombinations, it's quite small actually, only 18 lines of code, just several loops, one inside another, but same argument, same result. And this structure allows us to do something like this. This function find implementation gives us implementation based on its name. So the name is given, and the result is optional implementation. If there is no such implementation, then we're getting none. Otherwise, we can get the real function and we can call it. So this structure allows you to use all these functions one instead of another. Or maybe you can call two functions and compare their results. So it's very easy when they have the same interface. That's a very important idea when you use this approach when you implement algorithms. For the next part, let's look into the main file. It's quite a long one. It's more than 70 lines of code, and it uses plenty of external libraries. We'll look into them a little bit later, but now I'd like to show you how we can use this main file. Note that I'm using special structure for command line arguments here. It was implemented using the CLEP library. This CLEP library is one of the best libraries for implementing command line interfaces in Rust. So how can we use it? One simple way is as follows. Let's run terminal. And in this terminal, we can run cargo run, and then this program with help argument. This was generated for us by the CLEP library. Okay, and there is a help screen, and we can use it. Okay, let's look. This is our usage. We can provide size of the problem here. We can also provide list of implementations, one or another, and several flags. We've used this one, and then it can be verbose. Let's try to run them. Like for example, size of the problem is 8, and we want to run depth first search. Here is the result. We've got results in 1 millisecond. I didn't print results in this program because there are too many of them, but I'm just checking timing here. Or we can run the same algorithm with verbose flag, and with that we can get all the information about memory usage, and this was programmed there, right there. Okay, so let's remove this terminal here, and let's see what do we have in this main rs file. Okay, this is the structure for command line arguments here. A lot of magic, macros magic here, but it's quite easy actually to use, even if you are not Rust expert. Then I have a function report, which gives us timings, and timing is quite simple. I just check the moment before running algorithm and then after, and then see what's the duration between these two moments in time. And if it's verbose, then I also print a lot of information about memory usage. And main function itself, I'm creating arguments here, and then everything is parsed by the library. I'm not thinking about that. And then just some information with colors and stuff like that. Here you can see them by yourself. And we just run all the implementations in the given list. And in my example, we had only one. Then run, and then we call report, and that's it. So this is main function. Why is it a good idea to have main function like that for this task when we implement algorithms for the same problem? Because it's very easy to experiment. So once again, you can run two implementations and compare them. You can run one implementation. You can run all of the implementations. And it's very easy. You don't have to edit something in your program. You don't have to remember what implementation was built in the main function. You just specify command line arguments, and that's it. If you're using IntelliJ IDEA or Selenium, you don't have to remember all those flags for running cargo, run, and then release, debug, and stuff like that. It's very easy here because you can open run configuration from the menu, from the interface. For example, here I have something for running BFS with release flag to make it maximally optimized with some predefined parameters. Or I can define another run configuration which is not in release mode to debug something. Or I can define this one. And then I can run all these implementations without going to the terminal. So this makes you flexible. Many configurations, and you can easily run the one you need at this particular moment. And you don't have to edit your program to run what you actually need. So it's a main function which allows you to experiment with your program without editing again and again. This saves a lot of time, I guarantee that. Now let's talk about testing. As usual in Rust, we prefer to keep our tests as close as possible to the implementation. We call these sorts of tests as unit tests, and they test just one implementation. For example, here you have test module, which is coupled with breadth first search implementation, and it checks very small details in that implementation. We can run this test and see if everything is okay. Well, it's all right. We've passed the test, so that's just fine. Apart from these unit tests, we may have also integration tests. For example, here we have tests which belong to the whole project. It's a test suite which has two tests, one for smaller cases where I just check if the results are all right for small problem sizes like 1, 2, and 3. And look, I check here not the full results, but only sets. So I don't check order of the results. That's a very important idea. When you write tests, you want to make sure that you test what you actually need to test. It doesn't matter in which order elements come from this and that implementation, but the set should be the same. Apart from smaller cases, we also test on larger cases. We don't have reference results here because they are large, but we can compare two different implementations. Usual idea is when we write slow implementation first, it is usually quite simple and we make sure that it is correct. And then we try to write optimized version. And this optimized version can be fast, but it is very sophisticated. And if both versions give us the same results, like slow one and fast one, then we make sure that everything okay with our efficient implementation. So we can use the same practice here. We can run both integration tests using our standard mechanism. We can run corresponding configuration. Here is it. Both tests just passed, so everything is fine. When you have tests in your project, you can be sure that you write everything correctly. So it gives us an opportunity to optimize and to get another implementations which are also okay. And finally, benchmarking. Benchmarking takes a lot of time, so let me run it first and then I'll tell you something about that. Here is our benchmarking suite just for breadth first search. The idea is to check running time for one particular function many times, like thousands of times, and then to compare results. For example, here we can see, well, BFS for n equals to 5, performance has regressed a little bit. So we run it many times and then have this performance degradation. Maybe it's because we've done something wrong in our implementation. Maybe we just our computer was a little bit busy at this particular moment. So here I use Criterion library, which is very popular for writing benchmarks. It has a lot of abilities. It can draw graphs for you. It can explain many details. It gives you quite precise information. So please use Criterion. There are a lot of tutorials on using it, so I will not go into that here, but you have to try it at first. Well, remember, if you want to learn Rust, then you have to create an ecosystem for you. And this ecosystem should include version control. You should write several modules in library crate. You should write main crate with command line arguments to make all that stuff convenient to use. Then you should write tests. And of course, you should write benchmarks. Once you have all that, you're on the safe side. Just write your implementations, check them, make them correct. And as a result, you will not only learn Rust features, but you will also learn best practices in software development. And that's a win. This is all for this talk, and thanks for watching. Now I'm glad to answer your questions.